Okay, well, welcome back everybody, and in this video what we want to do is take a look in a little bit more depth at the E2 or the elimination reaction, and in particular look at some of the outcomes that we observe when we look at what the influence of that double bond, the energy and the stability of that double bond has on the outcome of the reaction itself. So now if we recall, the elimination reaction is in general this one here where we have a substrate of some kind. We've got a leaving group on the substrate, and we spent some time in one of the previous videos talking about what makes a good leaving group and some strategies for how to improve bad leaving groups into good leaving groups. We've got a base of some kind, and here we're focusing on the elimination reaction, so we're looking specifically at bases as opposed to nucleophiles, a solvent of some kind, but here we want to look at the E2 reaction specifically, so we'd use solvents that would favor the binuclear process, so things like polar aprotic solvents. We get an HB forming, so the conjugate acid of whatever base it is we're using to remove that proton, plus the leaving group with its full formal negative charge. And what we want to do here is take a look at some detail of what the influence of the relative stability of that double bond has on the outcome of this particular reaction. So now, if you recall, we looked at the stability of double bonds a little while ago, and we saw this was one of the videos that we posted as we were starting the second section looking at aromatic molecules. And here we looked at the trends that we observe in the stability of double bonds, and we saw in general that the more substituted double bonds are more stable. So if I draw an arrow across the top here, what we're observing is more substituted. In general, what we observe is the more substituted double bond is more stable. And if you don't recall this, we put all of this in a video some time back, and so you can go back and take a look at that. And so there's some more in-depth in the textbook in Chapter 7 as well. So we'll see what the influence of those trends have on the outcome of these E2 reactions. One of the other trends in stability that we observe in double bonds is shown here, where what we typically observe, what we do observe, is that in general Z double bonds are less stable than E double bonds. So E alkenes are more stable than Z alkenes. That is more stable than E alkenes. So E alkenes are more stable than Z alkenes by a difference of about 4 kilojoules per mole. So that's a significant difference. And here the whole explanation for this difference in stability really comes down to sterics. Right, those two methyl groups on the Z alkenes, those two methyl groups interact with each other, sitting on the same side of that double bond, and raise the energy of that Z alkene by some 4 kilojoules per mole. So that's enough to have a bit of an influence on the outcome of our reactions. So what we see here, for example, if we look at an alkene that could have more than one possible outcome, so here, for example, we've got a substrate. We've got sodium ethoxide that we're using as a base. That's the conjugate base of ethanol. We've removed the proton, again a pK of about 16 or so. We're using DMSO, that polar aprotic solvent that favors the bimolecular reaction. So we're going to favor strongly the E2. The sodium ethoxide favors E2. It's more of a base than a nucleophile. And what we can observe are two possible outcomes for this reaction. That's the E versus Z alkene. And here the E will be the major product. E will be the major product for this particular reaction. And again, that's from our observed stability of 4 kilojoules per mole. And I'll just remind you again, if we're looking at that stability of E versus Z, we get this from the heat of hydrogenation values of the double bond itself. So the heat of hydrogenation is how we measure the relative stability of these double bonds. And we find that the E double bonds contain less energy than the Z double bonds. They're more stable, and so that leads to this being the E alkene being the major product in an elimination reaction where we could have both an E and a Z alkene as being one of the possible products. And again, just to sort of represent this in kind of a graphical manner, we can sort of show this on a potential energy diagram, where we'd have the substrate here. And then the two possible products, one being the E, one being the Z, where there's a difference between them of about 4 kilojoules per mole. And here we've got two very similar transition states with slightly higher, two similar transition states, but just enough of an energy difference to dictate the outcome of this particular reaction, where the transition state to get to the Z, that is the lower energy one, is the higher transition state, because to get to that Z anyway, the substituents have to line up interacting with each other. And we'll talk a bit more about how things line up on those transition states a little bit later when we look at the stereoselectivity of elimination reactions. So here the energy difference between the E and Z is what dictates this outcome. We see observe the E alkene as the major product in reactions where we have more than one outcome that can come out. In this case, E versus Z, we observe E being the major product. Okay, so what we want to take a look at here next is the other possible regiochemical outcomes, the influence that these double bonds have on the relative outcome of these reactions, and in some cases how we can even control that outcome. So what we've got drawn up here is another kind of substrate where we've got a couple of possible outcomes. Where we've got a couple of different protons that we could remove in that key elimination step. So here, for example, we've got two possible protons where we're leading to what's called either the Zaitsev product or the Hofmann product. You see our textbook refer to this, and you see many other organic textbooks refer to it by these names after the chemists who originally sort of discovered and looked and quantified some of these reactions. But I think there's an easier way for us to analyze what's going on in these reactions, because if we look at the two possible outcomes, what we can observe is that one of our alkenes, based on our observed trends of stability of double bonds, one of our alkenes will be predicted to be more stable. And the other alkene that we produce, the so-called Hofmann product, is less stable because it's less substituted. And more stable is the more substituted, less stable is the less substituted double bond. And so now we can start thinking about this maybe even a little bit in terms of thermodynamic products. One of the products is more stable. That's the one we might be able to get under thermodynamic conditions. And if we look at the protons that we're removing on our substrate, we can kind of observe some differences in those protons that we're removing. If we look, we've got one of the protons that we've drawn here. That's a less hindered proton. It's much easier to access by the incoming base. It's just sticking out on that methyl group. No other groups to interfere with it. Whereas this proton over here, that's more hindered. Right, whatever base comes in to remove that proton is going to get past the two methyl groups on the other side, plus the other methyl group, so there's just a lot of crowding going on there. So now if we start thinking about it in those terms, then we could maybe even think about describing that as the kinetic product, where we're removing the easier to remove proton in one instance, the harder to remove proton, that is, would be the higher activation energy barrier, might be the one the other side. So how to control this? Well, let's imagine what that potential energy diagram would look like, just for the sake of drawing it out. And maybe we get some ideas about how to control it based on what we draw there. And so we start with our substrate. And we go to our two products, which are lower. The elimination products are lower in energy than the alkyl halide. And so we've got one product which is more substituted, which is lower in energy than the less substituted. By about 8 kilojoules per mole. By about 8 kilojoules per mole. And so then we connect the starting material, connect the substrate to our two products. And so again, our observations here would lead us, our observations on the parent molecule itself. Our observations on the parent molecule itself would indicate that we've got a less hindered, more stable, less stable. We've got a kinetic proton that we have product and a thermodynamic product. So removing the less hindered proton, the easier one to remove, is the less stable product. Easier to remove suggests the activation energy barrier to the less stable product must be lower. Somehow, and maybe I'll just do that in a different color to keep that all straight here. The activation energy barrier to the less hindered product, to the less stable product from the less hindered proton must be lower in some way than the activation energy barrier. It ultimately leads to the more stable product. And so we've got a slight difference then in that activation energy barrier, enough of a difference, really. That blue activation energy barrier is less than the green activation energy barrier. Blue is less than green, so we can control the outcomes of these reactions. So how do we control the outcomes of those reactions? How to control it? Well, we can control it a little bit, and we talked about this example when we introduced the idea of thermodynamic versus kinetic control. We talked about using, for example, a small, strong base. And slightly higher temperature. That would give us the thermodynamic product. Whereas using a large strong base would give us, at a slightly lower temperature, would ultimately give us the kinetic product. Well, what kind of bases do we use? How do we control the outcome of this reaction? Let's take a look at that. Okay, so what we have here are a couple of example reactions where we might be wanting to control the outcome of these reactions. We've got identical substrates. We've just highlighted different protons on the two identical substrates. And we're wondering, how do we control the outcome of this reaction? We're using a solvent, in both cases DMSO, that would promote the E2 reaction, so we don't have to worry about competition from the unimolecular process, and we'll talk a bit more about that next week. So we're using something that favors strongly the bimolecular process, polar aprotic solvent like DMSO. Really the question is how to control the outcome of this reaction. How to get the kinetic versus thermodynamic product. So I'll take the boxes away, and we just try and figure out what would we put above each of those boxes. Well, we said if we want to get the kinetic product, we want to use a large, bulky base of some kind. And one of the bases that's often quite successful for this is a T-butoxide anion. So this is the anion of T-butanol or tertiary butanol. Got that big, large, bulky T-butyl group with those 3 methyl groups sticking out into space. So there's a lot of steric bulk associated with those, with this particular base. It's going to easily find the least hindered proton, and in this instance you would get this as the major product if you use that large, bulky base. Now for something like getting to the thermodynamic product, we want something that's more easily going to get to the least, or to the more hindered proton, So we often use something like the conjugate base of methanol, methoxide anion. Conjugate base of methanol, much, much, much smaller than the T-butyl group, only a single small methyl group there. It can sneak in and get to the harder to get at proton that leads ultimately to the more stable and more substituted product. So there we observe this as the major product there. And so we can make selections that control the outcome of these reactions. Here we might even use a slightly lower temperature. We might use something like -20 degrees Celsius to control the outcome to that kinetic product. And here we might use something like 20 degrees Celsius, or room temperature, for example, to get to that major thermodynamic product, to allow that to go forward. So it's the relative stability of those double bonds and those trends in stability of double bonds that we observe having an influence on the outcome of the reaction. Okay, well, what other observations do we make about these reactions? So what if I look at the outcome of this particular reaction? What do I observe here? And so we'll just draw this underneath here so we've got space to look at both of them. So sodium methoxide, I'll just throw the counter ion in so we kind of keep track of what's going on there. Sodium methoxide, again, the conjugate base of ethanol. This is a fairly strong base, or fairly good base, and this favors E2 reactions. So it's not a great nucleophile. It much prefers to act as a base over a nucleophile, and DMSO as the solvent. And that also favors E2 reactions. That polar aprotic solvent favors those E2 reactions, and so we're not worrying about trying to get much competition with the unimolecular processes in this instance. And what we observe for this reaction there's two possible products that we can draw for this reaction. Two possible products, right? We have two protons that we can remove. We can remove the blue one here, or we can remove the green one here. Right, two possible elimination products. They can both generate the more stable E double bond, and they both got roughly the same number of substituents on them. But what we observe in this particular reaction is that the pathway that leads to the removal of the blue proton is by far the major. That's the major product. Well, why? What's our explanation for that observation? Why do we see that as the major? Well, if you recall back when we talked about alkene stability, we talked about what we called conjugated double bonds. Right, we talked about isolated versus conjugated double bonds, and we said that those conjugated double bonds were about 28 kilojoules per mole. So this conjugated double bond those conjugated double bonds are 28 kilojoules more stable than these so-called isolated double bonds. And you can refer back to that video that we posted a few weeks back now to get a little bit more detail on that explanation. Well, this is what we're observing with these double bonds that can come into conjugation with these aromatic rings. Of course, that aromatic ring, we draw them as 3 double bonds, double, single, double, single. We know, of course, they're more complicated than that, but that double bond on the substituent that's outside the aromatic ring can get some extra stability by being conjugated with that aromatic ring. So putting that double bond in what we call conjugation with that aromatic ring makes the whole system more stable. And so given the choice, under conditions that would favor the E2 reaction, we make the more stable product, which is the product that has that in conjugation, depending on what the other substituents are, but that can be as much as 20 to 30 kilojoules per mole of extra stability that influences the outcome of these particular elimination, the E2 elimination reactions. And every so often we'll see when we talk about the unimolecular process can influence the outcome of the E1 reactions. So the relative stability of the double bonds has a significant influence on the overall outcome of these elimination reactions. And so just even as we introduced it back in the chapter 4 material, when we started looking at aromatic molecules, it seemed like a strange little piece of chemical trivia. But here we can use it when we start talking about elimination reactions to rationalize and explain a lot of the outcomes that we observe. But even more usefully, we can use that chemical trivia to predict the outcome of certain reactions and understand a little bit how to control those outcomes just by adjusting the conditions. Even something as simple as the size of the base allows us to get very good control of these reactions. And so that's what we'll spend the rest of our time together in Chapter 7 talking about how to control the outcomes of some of these reactions. But for this video, we're going to leave it at that point there.